Swayam Prabha. Digital India. Educated India.
Hello students, welcome back to the class on pericyclic reactions. So far we have been discussing the things related to sigmatropic rearrangement reactions. And in the previous class, we have seen the 3,3 sigmatropic rearrangement reactions and the analysis of the 3,3 sigmatropic rearrangement reactions with the help of frontier molecular orbital method, right? So now it is time to discuss about the cope rearrangement exclusively. So why this has got so much of importance means, so those who are preparing for the IIT exam, IIT JAM exam or GATE exam or CSIR NET JRF exam, so you please be aware that definitely there will be a question related to this 3,3 sigmatropic rearrangement. And that too, today we will be discussing about the stereochemistry involved in the 3,3 sigmatropic rearrangements, that is with the cope rearrangement. So today's class is about the stereochemistry related aspects of cope rearrangement. So cope rearrangement and stereochemistry associated with it. So what is cope rearrangement means? So it is a 3,3 sigmatropic rearrangement or reaction. It is a 3,3 sigmatropic reaction which is driven thermally. It happens under thermal conditions and in a concerted manner. Right. So this we have discussed in the previous classes itself. So cope rearrangement is a 3,3 sigmatropic reaction where the sigma bond is migrating from 1,1 position to the 3,3 position under thermal conditions. So how this reaction is happening means, as usual, when all the other pericyclic reactions are also happening via a cyclic concerted transition state, so sigmatropic rearrangement reactions and that to cope rearrangement will also pass through the cyclic transition state. Okay. So now the question is, if this is the molecule which is intended to show the cope rearrangement, so the generalization can be done like cope rearrangement is shown by 1,5 dienes. So this is the basic example, core example for the 1,5 dienes. This is 1, 2, 3, 4, 5, 6. So it is a 1,5 hexadiene. So any 1,5 diene when subjected to heating may possibly undergo 3,3 sigmatropic rearrangement and the product will be this, right? So the sigma bond here is moving there. So this will be happening like this. How this transformation is happening means, it has to happen via a cyclic transition state. What you can see here is, so this sigma bond is slowly vanishing, moving here, and then one of the pi bond is moving here, and then this pi bond is moving here. So a 6-membered cyclic transition state will be seen where 6 number of electrons are also involved, and it comes under the category 4n plus 2 pi electron system. So first it transforms into this cyclic transition state, and then this cyclic transition state will give you the product like this. But what actually is observed in the case of 3,3 sigmatropic rearrangements or cope rearrangement is, the cyclic transition state will prefer to go in the form of a chair conformation, chair-like transition state. Why only chair-like transition state means when compared to the boat form, the chair form is energetically more favorable. Energetically more favorable. And also it adapts like energetically it is equivalent for a diradical system. So how it will look like means, so the sigma bond which was existing here previously will slowly be moving from here and forming here. So this is a cyclic transition state where this acts as one radical system and this acts as another radical system. So it is energetically equivalent to and symmetrically also equivalent to a diradical system. So that is why all the Cope rearrangement will be happening through a chair-like transition state. And this Cope rearrangement was developed by Arthur C. Cope is the scientist who developed this Cope rearrangement reaction. So Goldstein and Benson are the two scientists who first observed the chair-like transition state. Okay. So after this, so all the Cope rearrangement reactions were understood like it is passing through a cyclic transition state which is in the form of a chair-like structure. So the first example, if you want to see with respect to the stereochemistry in terms of the chair-like conformation means, so you take a diene 1,5 diene, in this case it is again 1,5 hexadiene, and if this molecule is having only one single substituent, if it is having only one single substituent at either of these positions, it can be either here or it can be either here, right. So now the question is, after rearrangement, that is sigmatropic 3,3 rearrangement, what would be the product? So how this is going to be seen in the case of the product? That means, what is the stereoselectivity? So Cope rearrangements are highly stereoselective, stereospecific or stereoselective in nature. Okay. So the reason can be explained via a cyclic transition state in chair-like form. So if there is only one substituent attached to this, while drawing it in the form of a chair-like structure, so the double bonds are here and here, right. So this is 1,5 diene and this is also 1,5 hexadiene. So now the single substituent, if it is present, it should be always mentioned in the equatorial position. So the substituent should be in the equatorial position while drawing it in the chair-like structure. So therefore, what is happening here? This bond is migrating here, this sigma bond is moving here, and this is coming as the new sigma bond. In the cyclic transition state, this R group is in the equatorial position. So this sigma bond is slowly moving from here. A new sigma bond is being generated here. So we will get this cyclic transition state. So once the reaction is done, so the product will be like this. The double bonds are now seen here, and then the R group is still in this position. So now how do you transform it into this one and show this stereochemistry around this carbon atom? See, if you observe here closely, around this pi bond, double bond, so there is a trans geometry, right. So this is in transposition. So therefore, the product will be like this. And how do you get the trans? So if the substituent is this way, then it is in trans. So the product is this one. So one thing we need to clearly keep in mind is, if there is only a mono substituent on the 1,5-diene at this position or at this position, under thermal conditions, when it undergoes the 3,3 sigmatropic rearrangement, you will get a trans configuration over here in the product. So that can be explained via the chair-like transition state. So while drawing the chair-like transition state, if there is only one mono substituent, so it has to be kept in the equatorial position, then all the things are as usual, right? What if there are two substituents? We will see that now. So if there are two substituents and both the substituents are cis to each other, either above the plane or below the plane, both of them are now in the wedge shape. So this is one R group and this is one R group, or maybe anything, right? So now the expected product here is this one, R and R. See, this with respect to this double bond is trans, and this with respect to this double bond is cis. That means you will be getting a cis trans product, right? So, and the percentage of this is 99.7%. So, what is the yield percentage of this one is 99.7%. So, to a minor extent, the remaining 0.3%, you can see this trans product. This is trans and this is also trans. So, a trans product will be only for 0.3%, while a cis trans product is about 99.7%. How this can be observed? Means, let's go with the cyclic transition state, and we already discussed like the cyclic transition state happens via a chair-like structure. So, while drawing the chair-like structure, so these are the double bonds. Now the question is, these two groups are cis to each other. These two groups are cis to each other. How to take it? Means, when the two participating groups are cis to each other, then while drawing the chair-like structure conformation, their relation should be either axial, equatorial, or equatorial, axial. So their relationship should be either axial, equatorial, or equatorial, axial. So if I keep the first substituent in the axial position, this is like this, and now this is in equatorial position, right? So this is equatorial and this is axial. So you can take it in the other way also. So here equatorial and here axial is also fine. Now it goes to the cyclic transition state. So this bond is slowly vanishing, and the pi bonds are moving like this, and new sigma bond is forming there like this. So here the group is in axial position and here it is in equatorial position. So this becomes the cyclic transition state. After the completion of the reaction, you can see a new sigma bond here. This is the new sigma bond, and double bonds are now here, right? So what is the stereochemistry with respect to the groups, substituent groups, is like this. So here you can see around this double bond there is a cis relation, and here it is a trans relation, cis trans, right? So that is what we have seen in the product. How much it will be means 99.7%. So this is the answer for such type of reactions. So now it is quite easy for you to solve any kind of Cope rearrangement. If they give this way, you have to see whether these two groups are cis to each other or trans to each other. If both of them are cis, right, so both of them are shown in the wedge presentation, so cis in nature. So if they are cis, while drawing the chair-like transition state, they should be related to each other in axial equatorial form or equatorial axial form. So then after completion of the reaction, you can easily derive to the product and the stereochemistry can be easily judged. So what if the substituents at the 3 and 4 position of a 1,5-diene is trans to each other? So their relationship here is trans. One is in the wedge form and the other is in the dash form, right? So when they are trans, so then while drawing the cyclic transition state in the form of a chair structure, the relationship between these two should be either axial to axial or equatorial to equatorial. Okay. So in most of the cases, equatorial is preferred. So there is nothing wrong, like if you put the substituents in the axial positions at both the positions 3 and 4 and then derive the product, you will get the same answer. And it is also not wrong and more suggested or preferred to show the substituents in the equatorial positions. So this is the chair form of 1,5-diene hexadiene, and now the groups are trans to each other, right? So what we need to do is we need to maintain either equatorial or axial. So let us have this equatorial kind of arrangement. Yeah, right. So how in the transition state they will look like? So this bond is slowly vanishing and a new sigma bond is forming here, and these pi bonds are delocalizing. So here this is the R and here this is the R. This is the cyclic transition state in the chair form. So when you come back to the final product, yeah, right. So what is the relation? Here this is like this and here it is like this. So if you see with respect to this double bond, it is in trans form, right? So with respect to this double bond also, this is in trans form. That means a trans-trans product is obtained as the major product. Trans-trans product is obtained as the major product. So how much it will be means it will constitute up to 90%. It will be up to 90%. So you can also get a cis-cis product. Convert this into this is trans and this is trans and this is up to 90%. Alongside you can also get cis product also approximately 10%. And cis trans also approximately to 1%. So these are the minor products and this is the major product, and the major product can be easily detected by using the cyclic chair-like transition state. So now we need to also see what if the substituents are different. So far we have seen with the same kind of substituents, whether both are methyl groups or both are ethyl groups or something like that are, right? So if the two substituents on the 1,5-diene at 3 and 4 position are different to each other, then what should happen? So how we need to take this kind of examples means, let it be a methyl group and an isopropyl group, right. So, this isopropyl group is bulkier and this methyl group is smaller when compared to this respective one. So, now we have to also look at the stereochemistry. If they are cis to each other, so that means both I am presenting in the form of a wedge, right. So, what should happen if they are cis? While drawing the cyclic transition state in the form of chair structure, so you have to represent one in the axial form and one in the equatorial form. So, now the question arises. So, whether the methyl group should be in the equatorial position or the isopropyl group should be in the equatorial position. So, always remember that. So, if the bulky group is there as a substituent, then it is preferable to keep it in the equatorial position. So, the bulky group should be in the equatorial position. So, now bulky group, that is the isopropyl group, is in the equatorial position and the lighter group, that is the methyl group, methyl substituent, is on the axial position. So, now it is quite easy to complete this reaction. So, this is the cyclic transition state and then the product would be like this. So, what is the relationship here? So, this with respect to this double bond is cis, right. Yeah. So, with respect to this double bond, this is trans. Yeah. So, this is the product. So, one more important thing we need to see here in identifying the stereochemistry, especially in the case of Cope rearrangement, is they can ask you in the reverse direction also. They will give the substituents at the termini of the double bonds and then ask you to identify the stereochemistry or relationship between those two substituents after sigmatropic rearrangement, 3,3 sigmatropic rearrangement. So, this is the best way to synthesize chiral compounds via a CC bond formation. So, organic chemistry has explored so many things and one of such beautiful thing is you can prepare a chiral molecule with the help of 3,3 sigmatropic rearrangement reaction. So, for example, if you have substituents like this, if this is the starting material and now you are performing a 3,3 sigmatropic rearrangement reaction. So, what would be the stereochemistry after the completion of reaction? So, here the groups has to come, right. So, what is the stereochemistry around this is the question, right. So, you will be generating two new chiral centers here. This is one chiral center and this is another chiral center. And how those two groups are related to each other, whether they are cis to each other or they are trans to each other is what you need to identify. And I'm again stressing you like, so Cope rearrangement and Claisen rearrangement, which fall under the category of 3,3 sigmatropic rearrangements, is very, very important. And you will definitely see a question out of these two in the exams, right. So, now what you need to see here is just reverse technology. So, you know how the after converting it into the this thing. So, what is the relationship here? It is a trans. So, now it should be trans. Here also it is trans, right. Yeah. So, this is the thing. So, once it transforms a pi bond is converted into a sigma bond here, this sigma bond is moving here. So what is happening here? Sigma bond is newly forming here. So here it is like this in the transition state. Now you have to connect this here. So what is these positions? This is equatorial and this is also equatorial. This is equatorial and this is also equatorial. So if both are equatorial, what should be the relationship there between these two substituents is trans. So therefore, we can simply put one of these substituent in the wedge form and the other in the dash form, right? So this is the stereochemistry. So you can even identify R configuration or S configuration over those two chiral centers, and you can see plenty of examples of this kind in the textbooks. A question may be asked here, like when you compare these two examples where a conventional 3,3 sigmatropic shift is happening in the 1,5 hexadiene under thermal conditions via a cyclic transition state, resulting in the formation of the new sigma bond, which is highlighted in the blue color at the 3 and 3 corner. And in the second example, there is a cyclopropane ring which is forcing the molecule to be in syn orientation to each other, resulting in the formation of a cyclic transition state and also the migration of the sigma bond from 1,1 to 3,3. So it is observed like the first reaction is slower compared to the second reaction. So the second reaction having the cyclopropane ring is much faster when compared to the first reaction. So the reason here is stated like, to form the cyclic transition state in the first molecule, that is 1,5 hexadiene, the terminal carbon atoms of the 1,5 hexadiene system must have to come close to each other, right? So in the case of acyclic 1,5 hexadiene, that is the example 1, the rotation on the C3-C4 sigma bond is always possible. So as it is free, so it is not bound to anything. So the rotation between the C3 and C4 carbon atoms is always possible. And the molecule can take several conformations in addition to the required syn conformation of the diallyl system. So usually, so as discussed in any of these reactions, the terminal carbon atoms should be close to each other so that the lobes which are involved previously in the pi molecular orbital will turn by 90 degrees and result in the formation of a sigma bond. Okay. So whereas in the case of second example, as the C3 and C4 carbon atoms are attached to another carbon atom and resulting in the formation of a cyclopropane ring at this point, so it restricts the rotations around C3 and C4 carbon atoms. Therefore, in cis 1,2 divinyl cyclopropane molecule, there is no such possibility as the C3-C4 sigma bond is a part of the cyclopropane and the two vinyl groups are also cis to each other. And there is a less entropy loss in going to the transition state, right? So whereas in the previous case, there is a greater entropy loss in going to the transition state. So because there is a possibility of C3-C4 bond rotation and the resulting conformations are also more stable compared to the syn conformation. So that is why there will be a greater entropy loss in the case of acyclic 1,5 hexadienes, and in this cis 1,2 divinyl cyclopropane there is lesser entropy loss compared to the first one. So in the case of cis 1,2 vinyl cyclopropane, there is additionally some favoring aspects are there. So that is the release of strain energy. As the three-membered ring is transformed into an acyclic product, there will be an enormous amount of strain energy being released. In the case of other cyclic 1,2 vinyl compounds, the loss in the strain energy might be less compared to the case of cis 1,2 vinyl cyclopropane. So this is a very important example to be discussed and understood at this point. So, okay. So, in the next class, we will see the oxy-cope rearrangement reaction, right? And also some examples if possible. We will solve those examples in the entire scope of cope rearrangement. Thank you.